works. All right, everyone. So welcome. We are going to talk about Ito's lemma here. This is the main topic of lecture 9. Before we do so, I'm going to recall some content here from previous lectures. Namely, first I'm going to introduce the integral as well as the differential notation, referring to stochastic differential equations. So that's going to be the main purpose. You've seen already stochastic integrals, and now you're going to see the basically the differential counterparts. Basically, this is just to illustrate again stochastic differential equations, as you will see. So you have basically the differential and the integrals of stochastic processes. We had already basically considering integrals. Then I'm going to focus on Ito's lemma. That's the main subject of today, so I'm going to just basically prepare it. You're going to see basically Ito's lemma for establishing the stochastic partial differential equations, so PDEs. Okay, this is basically the main purpose, describing their dynamics, basically mutually, for example, financial assets and so on. First, I'm going to start for simple Wiener processes. Okay, so as they are, why it works and how it works, because I need to construct this. Then, based on that, you're going to see some diffusions. Diffusions are specific stochastic processes, among others. The geometric Brownian motion is one of them. There is also going to be the so-called Ornstein-Uhlenbeck process. Technically, I looked it up. The German pronunciation is used, but those guys are from the Netherlands. But Orn means, come from mid-region, so it means eagle. Anyway, okay, so I'm not going to discuss this. I'm going to use basically the German pronunciation. And then we're going to look at Ito's lemma for two diffusions, and then we're going to see which is a specific case for the time component. After that, we're going to look at, this is not what I'm going to do today, but I'm going to present later on, this is part of this lecture, actually the $1 trillion stochastic differential equation. And this is not going to be presented today, so I'm going to basically do this as in form of an extra lesson. Okay, that was a lecture which was missing, and I promise you basically to do a video about that. So I'm going to upload a video. It's going to be 10 to 15 minutes or so, but it will be basically included into today's session. But it's basically, since I'm running out of time, I don't have time to present this, but that's going to be a little more practical oriented issue. Okay, let me check. So where basically it works, but it seems to work. So, all right, we're going to continue. Now, first, again, I will basically introduce the integral as well as the differential notation. You saw this already, so just, as far as integrals are concerned, just simply you can associate it with stochastic integrals. For example, you have a Wiener process, and you create some functions on the Wiener process, for example, the integrated Wiener process. You saw last time what it was. I basically finished that one. That was part of last time's lecture. Basically, let's say the process at time point t is supposed to be equal to actually the integral of the Wiener process with respect to time. So basically, time is the integrator. Okay, so that is basically typical integral notation. Now, you can express this actually also for the Brownian motion with drift. For the Brownian motion with drift, we saw this, basically I call it B at time point t is going to be basically some constant times time plus actually sigma times or the Wiener process. Now you might ask yourself, okay, where is the integral here? Because again, if I say integral notation, where is the integral? And the answer to that will be basically, this is just written down indirectly, so you're going to see that in comparison. Because what I'm going to do now is I'm going to express these processes in terms of their differentials, and integrating their differentials is going to be basically, yielding the process here. Okay, so first off, if you want to express it differently, so the two things are equivalent. So whether you answer, let's say, a question in terms of differentials or integrals, it's actually equivalent. So because if one is known, then the other is also known. But I'm going to show you basically what differentials are. So let's say, for example, I'm going to address this, and then you simply look at the infinitely small increments, so you can basically associate it with that. Because if you integrate that, okay, so if you integrate that, for example, from 0 to t or so. So let's say I'm going to call basically part of the integrator s, and then you would integrate that from 0 to t. That would be basically the process itself. Okay, so that is basically xt. So there it is. Okay, so it's written basically down indirectly, but differentials can always be given directly. Okay, so all you would need to do is just to differentiate those things. And that's it. Okay, so you can simply just skip the integral. So when you basically have that, okay, with respect to t, of course, time point t, all you would need to do is just skipping the integral, but you would need to change the integrator, because the integrator goes from 0 to t in this case without loss of generality. Okay, so the starting point is going to be 0 without loss of generality in most cases, of course. If that's not the case, then, but it's still, it doesn't really matter, because that's basically what the differential is. Later, you're going to see that basically comparing the two, so don't worry. I can also express the Brownian motion in terms of differentials. If I look at basically the increments, there are, let's say, infinitely small. So the infinitely small increments can be associated with differentials. Okay, so then you would need to basically just differentiate those components. Okay, so one is basically enough here, which the first one is going to be time, and the second one is basically would be the Wiener process itself. Okay, so you will have basically some Stitches integration in here. Okay, and the question is why? Because how you would go back to the other when you compare the two. So when you look at basically both the differential as well as the integral notation, again, how you express it is up to you. Both are equivalent, because once basically the differential notation is known, then also the integral notation is known, and vice versa. Once the integral notation is known, then the other is basically also known. Okay, but simply basically just skipping integrals. Okay, so if you wanted to get basically the integral notation now from the differential notation here, okay, so from here, all you would need to do is just integrate on both sides, okay, and that's basically how you would do it. So then you would come back to basically to the process that you saw at the beginning. If you do this, again, so this is basically what I did, okay, so technically I was developing the integral notation from the differential notation, as you see, okay, so you basically create the cumulative sum. That's what you do. Okay, so technically speaking, when it comes to applications, you create a cumulative sum, actually, because you have the increments of the process, technically speaking. All right, so if you sum it up, you have basically the process coming back again. But again, when you look at differentials are describing the increments of the process. And basically, if you know where the process is starting, and then you'd have the increments, then you also know the process itself. All you would need to do is just literally integrating it. Okay, so you integrate basically on the other side as well. This is again something which we have addressed before. So that was basically last time's lecture, and we saw basically that this is equal to, when you look at basically the increments, the process at time point t minus the process at the starting value, which is assumed to be 0 here in this case for the integrated Wiener process. Okay, at least almost surely. All right, so that's basically what it was. Okay, you remember that? So again, we were doing this basically. We were expressing this one in terms of the integrals. I was not using differentials, but you can express it basically using differentials. It's basically a matter of taste. I find basically the differential notation a little bit more straightforward, but again, it's basically up to you. Sometimes the other might be more appealing. All right. Now, when you do basically the same thing, when you basically integrate the increments of the Brownian motion, as you see, so these are the increments that are supposedly be infinitely small, you would get back the process. So this is going to yield basically the process at time point t minus the process at time point 0. Okay, and since basically the starting value is assumed to be 0 almost surely, this is simply just basically the process at time point t. Without loss of generality, by the way, okay, because that is always going to be the issue. Okay, you start integrating from 0, and then you basically move on. There is a constant, right? And then you would need to actually find the antiderivative of mu with respect to s from 0 to t, and that's going to be basically mu times t. So that's basically what you're going to get back. Okay, I'm going to write it. Okay, I'm going to present it first, and I'm going to write it down. Okay, then you integrate the other part. Integrals are additive, guys. So the integral of a sum is always going to be the sum of the integrals, because basically the integral operator is a linear operator, as you know. So then you have, again, a constant, basically, and then you would address the integral, or the Stochastic integral of the constant with respect to the Wiener process. Now, I'm not going to talk about that today. This was basically last week's topic, among others, looking at those integrals, okay? So how to address them and whatnot, and integrating by parts and all these things. So just look it up, okay? This is not basically what we're going to do today. The issue is this, okay? So of course, this is going to be equal to the process at time point t minus basically its starting value, which is supposedly be 0 almost surely. But when you basically, again, execute this operator, this is going to, you need to find basically the antiderivative of the function. The antiderivative of the function, okay, of mu with respect to s is going to be mu times s from 0 to t. So this is going to become, if you basically take the upper endpoint of that expression, that's going to be mu times s, becoming mu times t, of course, and then the lower endpoint will become mu times 0, which is going to be 0. So that yields mu times t, okay, so that basically this part, and then you have plus, and then there is the other, right? We were not discussing that, but this is actually what the issue was, okay, so you saw this, that was sigma times, basically, you could take basically sigma out from the integral, and then you have the increments of the Wiener process, which yield basically the Wiener process itself. So this expression is going to be the Wiener process at time point t minus the Wiener process at time point 0 times sigma, which I've forgotten. So there it is. Okay, so again, let me write it down again so to make it clear. Okay, how this works. Okay, so when you basically calculate those integrals, the first is yields mu times t, and the second would be sigma times the Wiener process at time point t minus sigma times the Wiener process at time point 0, but it is going to be 0 almost surely. So this is basically what it's going to be. All right, and then you would get it back. So I'm talking about this one, okay, not the previous one. All right, so whether you're using basically the differential form or the integral version, it's up to you. Actually, both answers, I would be accepting it. Okay, so, but that's basically what a stochastic differential equation is. All right, so that's basically a partial differential equation if you have multiple, basically, derivatives, I mean, regarding basically functions, but I'm going to say this is just a differential equation. Okay, next week we're going to talk about how to solve them. In particular, basically, some specific types, but I will need to prepare that, and Ito's lemma is going to play a crucial role, especially basically where Wiener processes are involved. Anyways, okay, so first off, I'm going to review. This is a review, guys, so forgive me if I'm basically accelerating this. Quadratic variations of Wiener processes. We were talking about that. The quadratic variations of Wiener processes were finite. So what I was basically I would like to summarize here is that actually, I mean, when you look at quadratic variations, so that's the notation that I used, okay? So basically, when you have basically the Wiener process, that's going to yield, which is going to be a finite one. This is actually, so when you have t there, this is actually, or this was actually t. That's what the quadratic variation of the Wiener process was. I'm not sure if you're recalling it. Anyway, if not, then I would basically make a reference to it. Okay, so please watch the lecture. I think it was lecture 4, but I'm not sure. Okay, so that was basically one of the first times where I was looking at it. All right, now you always have a partition, so that's something which you're already familiar with, I hope at least. And then you have the interval from 0 to t. Okay, so that's always going to be the interval that I'm looking at. And then I'm going to basically address the quadratic variation of the Wiener process. Okay, so first I want to make a statement that all these endpoints are in order, right? So S0 is less than S1 and so on. And the last one is going to be Sn. And that is actually the upper endpoint of the interval, and S0 would be the lower endpoint of it. All right, so you're familiar with that. So, of course, and then you have the Wiener process, and I was proving that. So that was, it was not difficult, but it took a little while. So when basically addressing it, the quadratic variation is actually, I mean, you can call it like that. So that would be the I mean, this is the quadratic variation of the process, right, itself, but I was looking at the limit of the quadratic variation of the process. So the sum of its squared increments, right, on that partition. Okay, but keep in mind, basically, as n tends to infinity, okay, actually the subintervals are getting smaller and smaller and smaller, and the question is what happens to it. And there is going to be a limit of that, so we basically was addressing it. The limit in mean square, right? Okay, so you basically, I hope you remember this, as the number of subintervals increase, right? And that was finite. So the quadratic variation was finite. Usually I was expressing it like this in terms of the integral notation. So the integral of the square of the infinitely small increments of the Wiener process, because that is basically what I was using, okay? And I was calculating it. And we were doing it and blah, blah, blah. It took a while. And we had t coming up, okay, as I mentioned before. So that is basically indicating now, of course, if this is finite, which is supposed to be the case, but not zero, this means that the absolute variation of the Wiener process is not going to be finite. So the total length that the process is generating is going to be basically not finite. Okay, so that is a very important property that we already seen for the Wiener process. So even if you break it down, okay, so if you increase the frequency of the process, it's becoming longer. Okay, and it grows beyond any limit, okay, but not the quadratic variation. So the basically some of the squares of the increments are not, okay. So, but again, you can also write it like this. So I'm going to basically come back to the issue where I would implement, you know, the integral versus the differential notation. This is new, but actually you can see it right away. These two are equal. Okay, as you see. So, and that looks nice because you can see that basically this is equal to that. And that's going to be crucial. So whenever you see a square of increments of the Wiener process, right? Okay, in terms of the limit in mean square, sorry. This is always can be associated basically by the increments of time. Okay, and that's basically the major result which I'm going to evolve around today, because as you will see, Ito's lemma will basically play a huge role regarding it. Okay, so let me just basically make that statement so you can see this over here. Okay, so whenever this comes up, the square of, in this case, let's say infinitely small increments of the Wiener process, you can associate it with basically the increments of time. If you remember that statement, then you will understand the bunch of formulas I'm going to basically develop today. And I mean, Ito's lemma is also basically based on that statement, okay? Because due to the fact that the quadratic variation of the Wiener process is actually finite. All right? Okay, but that's basically what it would be. Okay, now when you look at the integral notation, which is already here, okay, so that's the integral notation, or you can basically take those two, okay, it doesn't really matter. I was basically doing both. So this is the integral notation. Okay, so those two are basically, again, this is the one here. Okay, so simply just writing it down is equal to that. Okay, and now since you have basically integrals on both sides, okay, of the equation, you can simply just skip them. All right, so and then you would basically get the differential notation. So you can simply just, you know, clear it, write this. Okay, it's not very practical because you have s as the part of the integrator, which I would change to t, okay, because you're integrating basically between 0 and t, so on at intervals. But again, it doesn't really matter how you call basically time. You can simply keep it as s if you like. So it doesn't really matter whether basically it's s or t or so. Okay, so again, to get basically the differential notation, you can simply just basically dismiss the integrals, and then you would basically get the differentials equivalently, okay? So that is also symbolic notation, by the way. So because these things do not exist, okay, but they basically can be treated in terms of a differential equation. So that is a stochastic differential equation that you're going to see, okay, on the slide. So when you look at basically the differential version, okay, the differential version is here. And that's basically what I call the stochastic, okay, so stochastic differential equation, okay, SDE. Do you understand this, guys? Okay? All right, so later on we're going to basically talk about how to solve them and whatnot, but that's not basically the topic of today. The topic of today is going to be basically looking at those differential equations in terms of Ito's lemma and so on. Okay, now the first statement I want to make, which you're probably familiar with, so people kind of sometimes when I basically introduce you to this concept of differentials, people sometimes are struggling with that. But that concept has been already done when you look at you look at differentials of deterministic functions. Okay, that's the limit, by the way. So you can see here, this is it. Okay, so that's a quadratic variation. Looks nice, okay, as you see. And let me generalize that for a moment, so because this is also part of it. Okay, here what you see is not going to be the Ito integral. That's not basically the limit of the Ito integral. Why? Or Ito sum, you can call it like that. Why? Because you have the square here for the increments. That's one of the reasons. And the other is basically that Si asterisk is going to be some middle point between Si and Si minus 1. It doesn't need to be a middle point, but it can be basically anywhere. Okay, so those are the two reasons why it's not an Ito integral, by the way. Okay, but I haven't made that statement. So if you basically, again, assume that basically Si asterisk is some point between Si and Si minus 1, I will fix that one because there is it's not an error, but it's inequality. Right? Okay, so you can also basically equate that to be the lower endpoint as well as the upper endpoint. I apologize, I will fix that. Okay, so that is an issue which I will need to address. Okay, but after that, okay, when you address the limit, so that's going to be it. Okay, so not a big deal, as you see, because I was taking basically the previous part, and that was not actually the Ito integral, by the way. This is a Riemann integral, as you'll see. Okay, so that is actually what you'll have here. Okay, so which is an interesting result. Okay, in terms of stochastic integrals, you would write it down like this. So you have the Wiener process, and then the square of the increments of the Wiener process. That's it. That's not the Ito version, actually. Okay, what you saw. Anyways, okay, now I'm going to take another function, which is going to have certain properties for that integral to converge, okay, which I basically look at, basically the integrand is recalculated by that function, okay, so you can simply just do it. But that will only work if the function is actually continuous on the interval, at least almost surely. So it's not basically always there, but I mean almost everywhere in this case. It's a deterministic function. Sorry, it's not a stochastic one. It's a deterministic one. Okay, so it would be basically continuous almost everywhere. Because then, of course, the corresponding Riemann integral would exist. And then, of course, in this case, based on that, is basically the Riemann-Stich's counterpart of some sort. But again, you have a function of the increments here applied, and that changes a lot. Anyways, okay, so that's going to be the quadratic variation, not of the Wiener process, but a function of the Wiener process. So here you have a function of the Wiener process, actually, and that is basically generating this type. Okay, it's very easy to deal with that, okay, but yeah, that's it. Okay, so on the one hand, basically you have a quadratic variation. On the other hand, basically a function of the Wiener process. Anyways, yeah, so that's it. Okay, so this is not basically a big issue. Not to prove this, you can do the same thing, where I was basically addressing the quadratic variation of the Wiener process, but I'm not going to, so that's basically a little extension to this. Now, based on that, I'm going to make another statement, because again, in this case, as you will see, okay, nothing would change. So let me go back, instead of basically looking at, let's say, the quadratic variation of the Wiener process as to be the integrator, since basically that is, you know, having that limit, if you say, okay, then you can simply just change it basically and by the increments of time, because that would be generating the same limit. Okay, so that's an interesting one. This is actually a Riemann type stochastic integral, as you see, and that is basically it's going to be its limit, by the way. So if the function f is continuous almost everywhere, right, then it will work. Okay, so that is actually a statement that I was trying to make. You could replace that expression by, let's say, the quadratic variation of the Wiener process, where, okay, which I write it like this, so that would be it, okay? Which is basically the square of the increments on that partition for the Wiener process, okay? And that is going to be the same limit, by the way, so, which is not surprising, because the quadratic variation of the Wiener process is finite, okay, and positive, okay, all right, in general. Now, I'm going to look at basically the differentials, because again, I was mentioning before, most people are kind of struggling with that concept. And let me make that statement. This is not going to be relevant for the exam. This is basically based on a Taylor series. So let's say you have a function, and the function is supposed to be infinitely and continuously differentiable. Now, what does that mean? This means that you can differentiate the function as many times as you like. What you're getting is always going to be a function that is continuous, at least almost surely. But again, I'm not, or almost everywhere, sorry, but I'm not, again, always adding the term almost everywhere to it. So if you want to, you can simply just ignoring it. But you should know that it's not only working for functions that are continuous, but continuous almost everywhere, which means that, actually, if you're not sure, which means that basically the number of points on which the function is not continuous is countable, okay, technically, okay, because the length would be actually 0. Anyways, okay, so when you express basically the differential of the function, let's say at time point t is just an argument, okay, not necessarily time or so, but you can basically associate that with time if you like, because that's always on the x-axis, at least when it comes to time series. This is basically what it's going to be, okay? So you have the derivative of a function, which must exist, okay? It must exist because the function, it's not just differentiable, but it's continuously differentiable. So it have basically continuous derivative, at least almost sure. And that's basically the notation that you probably saw. Because according to the Leibniz notation, so when you write basically the derivative of a function in terms of a Leibniz notation, this is, I mean, you can basically express this in terms of a ratio of two differentials, although basically this is just a symbolic notation. So when you basically, let's say, quote unquote, you solve this equation for the differential of the function, which is describing the change of the function, right? You simply have basically its derivative attached to the differential of the argument of the function, you see? So that is consistent in that regard. But due to the fact that this is true, I want to basically show the equality for that. This is actually a differential equation, not a stochastic one, a differential equation. And you could confirm this by simply just basically taking the integrals on both sides. All right, so that will be one way to do it. Okay, but this is something that I'm not going to. Okay, so that's not what I'm trying to do. I want to confirm this relationship. Again, it's intuitively clear. Actually, in this case, the function does not even need to be infinitely differentiable. It needs to be just differentiable at least once, right? But since I want to try to explain this by using the Taylor series expansion, okay, around basically a specific point, and you're going to see where, because I will going to use basically partition on an interval. Okay, the Taylor series works like this. So when you have basically a function at time point x, and it's infinitely and continuously differentiable almost everywhere, then that is going to be basically the limit of the sum of the following expression. So that's basically the limit of the following expression. So you can look it up. I mean, I'm not sure if you've seen this before, but if not, it's not going to be an issue. Let's say the nth derivative of the function. So that's notation this is the nth derivative of the function. Okay, so that's the first derivative. You can express it to be f, and then you put basically brackets, and then you write 1. So that's going to be the first derivative, right? So because there is, the derivatives there which are indexed, so you'll see basically what it is at point A, around which you perform basically the Taylor series. So, and then the factorial of n divided by the factorial of n. So you basically calculate the nth derivative of the function at point A, dividing it by the factorial of n, and times x minus a to the power of n. So that is basically how you can express this. okay? So if the function is infinitely and continuously differentiable, then there is a possibility to write it like this. And let's assume that basically this is the case. So I'm going to do that, okay? So just ignore basically differentials above, okay? So the function, because I will basically incorporate that into the partitions, okay? So that you will see. So the function at time point Si, which is basically the upper endpoint of the ith subinterval of the partition of 0 and t, again, so that is corresponding to x, and then the lower endpoint, so x is going to be Si, and a from this formula is going to be basically the lower endpoint of the ith interval or the ith subinterval of the partition of the interval from 0 to t. Okay, so then you'll see basically how I'm adjusting it. So you're going to get basically, in terms of the Taylor series, this is going to be the function at point Si minus 1, why? Because the zeroth derivative of a function is going to be the function itself, right? So you don't differentiate the function at the beginning. So this is basically the issue, because the first index is 0, and then you divide it basically by the factorial of 0. Now the factorial of 0 is equal to 1. Of course, you could skip it, but I will keep them anyway. So then you see basically what I do. And then whatever basically to the power of 0 comes up, if the lower and the upper endpoints are not equal, which there are not, okay, there aren't, sorry. So Si minus 1 is strictly less than Si, then this is going to be 1 as well. So basically you could just basically write down the function at time point, at time point Si minus 1, which is the lower endpoint of the ith subinterval of the partition. But I was doing that anyway. Okay, next I'm going to basically take the first derivative of a function at the lower endpoint of the ith interval or the ith subinterval of the partition divided by the factorial of 1. Okay, so this is how it goes, times, again, the upper endpoint minus the lower endpoint to the power of 1, okay, as a whole. You can also basically, skip this exponent here, right? So this is not important, okay, but I'm going to keep those things anyway, okay? The factorial of 1 is equal to, you know what the factorial is. I forgot to basically to ask you this, but if you're not sure, the factorial of n is equal to n times n minus 1 times n minus 2 and so on times 2 times 1, right? So you basically have that, okay? Now, the next I'm going to basically, you'll see how the Taylor expansion works. You have the second derivative of the function at the lower endpoint of the partition divided by basically the factorial of 2. The factorial of 2 is, of course, 2 times 1. So that's not a big deal. Anyways, okay, so, and this is basically how it goes. Of course, you have the square of the difference, okay? Here comes, so that's going to be the case where you see some sort of quadratic variation. I wanted to basically remind you on that. So I'm going to change that by the Wiener process, and then you will see that, okay? But that's not what I'm going to talk about here. So the reason why I was using those things is because I want to basically illustrate the validity of the statement that I'm going to make regarding the Wiener processes, okay? Is it clear now? So far, so good. Again, so this is just, again, a deterministic function. It has nothing to do with stochastics at all, okay? But you could address those things. The first, I'm going to make this factorial 0 disappear and so on. Then I'm going to basically subtract on both sides by the function at the lower endpoint. So then it's going to be on the other side. So here you see basically the increments of the function, right? And and that's basically the same thing. So it's nothing new, but that comes from the Taylor series. And then I'm going to look at basically the limits of those things. Now the issue is, keep in mind, there is no limits here because all those things are actually converging to 0. So as basically the number of subintervals increase, okay, that will converge to 0, that will converge to 0, that will converge to 0. However, the corresponding series will not. Okay, so that's the point. So think about it basically in terms of that there is some sort of a cumulative sum here. Okay, because if you have the sums, They will not the series will not converge to 0. The corresponding members from the sequence of the series will do, but basically the sequence is not necessarily. I mean, some of them will, but not so necessarily. Anyways, okay? So I'm going to basically express those things in terms of their differentials. Okay, not the integral notation, but the differential notation. Again, this is, again, expressed by the infinitely small increment of the function. And I'm going to write down s, okay, in this case. So I'm going to call it basically s. You see? Okay, and then of course if you, the real notation would be that you have the sum here from the first to the last, okay, element of the partition, and that will converge to the integral from 0 to t. That's it. Okay, so that makes more sense. This is more, let's say, sophisticated in that regard from a mathematical perspective, although this is not very clean, all right, in that sense. But I'm going to basically express those limits in terms of differentials. So again, the limits are basically again, so I would need to basically address sums, and then you would have integrals coming out for the limits, but I'm going to express them in terms of differentials, okay, which makes more sense. So in this case, this is going to be the first derivative at point s, okay, so that will basically call the integrator, and then you'll have basically the corresponding limit. Again, same thing, if you had a sum here, that sum would converge to this integral. And I'm going to express it in terms of the differential notation to make it a little bit more accessible in that regard, okay? So don't keep that in mind, guys, when you look at it. I'm expressing limits of integrals now expressed by the differential notation, not the integral notation, because I'm lazy, okay? So I don't want to have those sums and integrals and all that stuff. It's not necessarily the case. Okay, now what happens to that? Again, think about it. When you have a sum, that would correspond to basically converge to an integral under a certain circumstance. And the only circumstances, I mean, of course, in this case, it will be quadratic. So this is 1/2 times the integral. Sorry, I mean, okay, in terms of basically differential. But here you see the quadratic variation of that. And I was addressing this already. So that was basically, I think, lecture 4 or 5. Look it up again. You can check it out. So the quadratic variation of the identity, I was looking at it. Okay, so the quadratic variation of the identity, here you have square, was 0. All right, remember that? Okay, so that is basically, that was one statement that I make. Okay, I mean, so the absolute variation would be finite anyway, so in that regard. So yeah, in this case, this expression is going to be 0 now, at least for now. But when I replace or incorporate the Wiener process, it won't. Okay, so that's going to be the issue. But here it is. Okay, so this expression is 0. And all other expressions are also 0. But you could also basically list it there. So you have 1/2 times the second derivative at time point t, where you have the square of that differential. And then the next expression would be, so if that would go on, 1/6. How come 1/6? Because the next expression would incorporate the third derivative at the lower end point divided by the factorial of 3, which is 3 times 2, so that yields 6. Okay, you understand? Times the third derivative at time point t, and then you have basically the cube of that differential, which is also 0. I mean, not just in abstract sense, but in literal sense, because that integral, so the corresponding integral would be 0. You understand the point? So that will go on, but these things are 0. Okay, and basically when it's written down in terms of integrals, so that is basically 0 because it's already here. Okay, you understand the point, and the reason is not because these differentials are 0. That's not true. The corresponding integrals are. So I was basically addressing that. Again, keep that in mind. But now I'm going to use the differential notation, which is a little bit more practical because I don't need all that sums and integrals and all that stuff. Again, so basically the quadratic variation of the identity, you will see, okay? That was, again, look it up, that was 0. So I was talking about the integral that is 0, not the differential, actually, although basically, because these differentials don't exist, okay? These are the infinitely small increments from the corresponding integrals, that are taken, or just simply again, use the notation here. Okay, so that's basically it. Understand the point, guys? Okay, so this is basically where it comes from. Again, and after that, all of them are going to be 0. Not the differentials, the integrals. Okay, so all of them will converge to 0. So that's the reason why basically, regarding the Taylor series, only that expression is going to be relevant. Okay, so let me just basically make that statement again. So maybe you understand this better. Only this expression is going to be relevant. Okay, and then you'll see that basically this is it. Okay, so here it is. So this integral from 0 to, okay, I got s here, so you can write it down. T, okay, is going to be actually the limit. So it's not equal to that because this is basically what it would be. Okay, but that is going to be the limit of this sum. Okay, so you have basically the sum here, which will again converge to the integral from 0 to t. Now it's fine. Okay, so I'm going to take this away. Okay, so then you see basically what it is. Okay, and all other sums or series, let's say, will converge to 0 if the function is infinitely and continuously differentiable on which you perform that. You understand the point? Okay, so that is basically the issue here. All right, yeah, now, if you do this on a Wiener process, it's going to be different, very much different, okay? And that's what I'm basically talking about. Because this differential, or the integral, the corresponding integral, all right, so here, is not going to be 0, and that is going to be the difference, okay? So, because you have the square here, all right, so, but you're going to see that later on. Okay, for deterministic function, it is. Okay, now, let me recreate that statement, so I'm going to rearrange that thing, and then you'll, basically what you have is, I'm going to replace that function by functions of Wiener processes. Okay, so what you have is not f of t, but f of the Wiener process at time point t. Okay, so you have some certain functions. I was introduced you to 7 or so, if I recall it correctly. Okay, now, so what I mean by that is this. Okay, so you have basically the differential at time point t, but not at time point t. You have the Wiener process at time point t, and that is it. Now, accordingly, you can apply those statements, but the only thing that will change is this expression. So please mind that expression when you look at it, because that differential will not be neglected as it is basically for the Taylor series expansion for deterministic functions. And the reason is because the Wiener process has a finite quadratic variation. So that's going to be the statement that I'm going to make. Okay? So here you're going to have the derivative of the function at the Wiener process at time point t, and then basically a differential attached to it, and then of course the quadratic variation. So the next one, again, based on this expression, again, I'm going to change that by the quadratic variation of the Wiener process, would be 1/2 times the second derivative of, at the Wiener process at time point t. The Wiener process is not differentiable, but basically the function f is. And then you have the quadratic variation of the Wiener process, or the differential of the limit of the quadratic variation. That's the correct term. But that is, again, you saw, is equal to delta t dt now. Okay, and that's going to be the difference. Not so that this expression will not be neglected here. Okay, and that's basically the issue. Anyways, okay, so you have 1/2. And that's, this is how you evolve. And dt, why dt? Because, again, okay, so in terms of a differential equation, this is equal to the quadratic variation. Okay, so I'm going to rewrite this, apology, in terms of the quadratic variation of that differential for the Wiener process. Okay. Ghosts are coming here, right? Yeah, this is it. Okay. What was that? Is it just me, or you heard that too? Okay. Oh, the windows was opening. Okay. All right, at least. Okay. Okay, now I'm going to change those things by the Wiener process. Here you see. Okay, now I'm also need to change the convergence because the convergence is in mean square now. Okay, so when it comes to stochastic integrals, remember that. Okay, but that's the issue. Okay, so when it comes to stochastic process, you can adopt this, but the only thing that will basically change, again, here you see basically the increments of the Wiener process. These things will converge in mean square. Okay, of course, in terms of their sum. Okay, now here, the E2 integral can appear, it did not, but basically it can, okay, because in this case, the increments are also going to be changed, okay, here in this regard. Okay, so that needs to be addressed here, okay, because mind you guys, the exponent here is equal to 1, not 2, 1. So that is the increment of the E2 integral, right? Okay, or you can call it basically differential of the E2 integral. You see? And that's why I'm writing minus here to basically to illustrate that fact. Okay, but you don't need to. Okay, so when it comes to differentials, you don't need to. Okay, but I wanted to basically have that written down for a moment. You might remember that. Now, in this case, I'm going to do the same thing. Here you see some quadratic variations, and then you'll have convergence in mean square. But keep in mind, guys, it's not the differentials that they converge. It's the integrals that they do, because the series do. Okay, and now, if you replace that, okay, so you can see, you don't need to replace these things. You don't, because, again, quadratic variation of the Wiener process is finite, right? You see? And then whenever basically quadratic increments of Wiener processes are around, you can associate it basically with the increments of time. I told you that one, all right? So and that's basically what is happening here, okay? And then, of course, you have the sum. So basically, let me make those statements again, basically correctly, because this is basically the correct statement, but I wanted to summarize here. If you take the sum on both sides, you have the sum basically from the first to the last part of the partition. That will converge to the integral from 0 to t of this expression. This is the E2 integral, by the way, as you'll see. All right, because it's basically the exponent is equal to 1, and you have the lower end point here for the Wiener process, even if it's basically altered by the function. It doesn't really matter. You see? So that's the E2 integral here at the beginning. And we were also, again, if the function is equal to identity, so f is equal to identity, the integral becomes 1/2 times the square of the Wiener process time point 1 minus t by 2, right? So that is basically minus 1/2 times t. Anyways, I'm going to make that statement over here. So that's basically what the previous statement was, okay, which I was using. Okay, so here you have actually the quadratic variation of a function of a Wiener process converging to this integral, okay? You can take 1/2 out from the integral, which I didn't, but you can, of course, right? And now you see the analogy here, guys, okay? And that is the issue why basically you will not dismiss this differential here from that equation regarding the differentials of the increments of the Wiener process, or basically the infinitely small increments of a function of a Wiener process. Let me correct that, okay? You understand the point? So that's basically what Ito's lemma is claiming. And we were just proving it, okay? But I was basically proving it, so that's not the original version. This is a version that I altered because I was putting a lot of restrictions on the function, okay? So that's the first statement that I was making, okay? So we have the, as basically, based on that, so this is basically the base, all right, for that statement, expressed basically in terms of differentials. And we were just proving it using Taylor series expansion. However, the issue was that I was proving it with a very, let's say, sufficiently restricted or constrained function, which is supposedly be infinitely and continuously differentiable. And to be honest, guys, again, even if it's basically almost surely, it's not the case for most functions, all right? Especially not basically in finance. So, however, it would not work in practice, but it's much, much easier to prove, Okay, so that's the reason why I decided basically to give a little intuition here based on that. Okay, but again, this restriction is, let's say, relatively harsh. So I would need to basically relax this a little bit, but I'm going to show you how to. Okay, but I took it basically because it's much easier to prove. Okay, so you don't need to know about anything, just maybe the Taylor series and the quadratic variation of Wiener processes, and that's it. Okay, so you can basically just put those things together. And then the statement is here. So that's the statement. This is Ito's lemma, by the way, okay, for Wiener processes, or actually for functions of Wiener processes, but again, or the increments of that. Anyways, okay, so that's basically the issue. Again, you don't need to refer to the Ito integral basically here in terms of that differential, as you see. Okay, you see that issue? Because, you know, at time point t, it's always at time point t. Okay, so you don't need to basically to underline that statement, but you can. Maybe it would be more consistent anyway. Okay, but I'm not going to. Yes, so that is basically differential from the Ito integral, actually, which is here. Okay, so here, down there, you got it, but here, the reference that is supposedly be the lower endpoint, it's not. Okay, so that's it. This is the statement, and we just proved it. Okay, so that is the issue with Wiener processes. If the function is deterministic, so you don't have, let's say, the Wiener process, right? Okay, you don't have it. Let's say you have a deterministic function that you saw, that this is no longer there. Just a moment. This one is not longer there. Because in that case, though, this integral is 0, okay, which is not there. This is not it. Okay, so this is not it. But because in this case, you have the square of that, so this is going to be 0 in that regard. So that's the only difference. So that's why basically that differential is not there for deterministic functions. But since the Wiener process has a finite quadratic variation, it's not going to go away. All right, you understand the point now? Okay, so that is it, guys. Okay, here you have it basically in terms of the integrals. Okay, so those are the integrals here. Okay, and those notations are corresponding to each other. Let me stress that. So you might not see it, but I'm going to basically illustrate that. So this differential here corresponds to this integral, right? This differential here corresponds to this integral. Again, these are not the same things, but equivalent in terms of their notation. And I haven't written that down. But what would that be? This differential to which it would correspond to basically the function of the Wiener process at time point t. Why? Because the Wiener process at time point 0 is 0. But you could basically, you know, look at that increment as well. So you can simply just calculate the function. At point 0, it might not be 0, right? But that is it. Okay, you see? So those are the things that they correspond to. Because if you, let's say, you take the integral of that from 0 to t, you will get basically the function at point of the Wiener process at time point t minus a function at the Wiener process at time point 0, which will be actually 0 then. All right, but that's it. Okay, the differential notation is actually more practical in terms of expressing Ito's lemma. It's more common also, but again, since it can be also expressed by basically the integral notation, I'm going to do the same thing. Now, before I do so, I'm going to look at a little restriction which is not that harsh as the previous one. It also works if the function is only twice differentiable. So only the first two derivatives are supposedly be basically existent, which are continuous almost everywhere, and that statement will work as well. So in that regard, that will also work. Okay? So the function does not need to be infinitely many times differentiable. Infinitely differentiable, that's the term. It's enough it's twice differentiable. But if it's just twice differentiable, so the third derivative might not exist, okay, then I could not basically do the Taylor series expansion that I did. I would need to look at the remainders. And that's a little bit difficult, more difficult to prove. But it's not impossible. I was basically preparing that too. Okay, so again, you would need to relax that assumption, but at least the first two derivatives of the function supposedly be existent. Okay? The function is not necessarily infinitely many times differentiable, but at least twice. Okay? So the first two derivatives are basically, must be actually continuous almost everywhere in this regard. Anyways, okay, so this is a statement, okay, and I'm going to write it down in terms of integrals. Okay, so that's a differential notation, you see? Same thing. And then I'm going to express it, which is more common, in its integral form. So how would you do this? Again, in this case, on the left-hand side, you have basically the increments of the function of the Wiener process, right? The Wiener process at time point 0 is 0 almost surely, but the function might not be. Okay, so that's why I was basically writing it down. And then you take basically the differentials. I was basically changing the integrator from t to s, and then you integrate from 0 to t, and that's basically it. Okay, here is the integral, and then you would integrate from 0 to t, and that's the equivalent of the differential notation. So that's the differential notation here, and its equivalent is the integral notation. Okay, most people find the integral notation not very practical, so that's why basically they use the differential notation. But you should know that these things are equivalent, guys. Okay, and you might be basically confused here. Why is basically this expression the integral version of that? Because if you calculate basically that integral, and let me just do it. Okay, so you see, maybe you see it better. So the integral of those increments, okay, here you got the Wiener process. Okay, you see, let me just do it right there. All right, so here it is. Okay, this equals actually from 0 to t, right? This equals, s is the integrator. This equals the function of the Wiener process, sorry, at time point t, as you'll see, minus that one. Okay, so you can see that basically those two relate to each other as the others do. Okay, you understand it now? So again, keep in mind, guys, this expression is the integral version of that one. You understand that, right? Okay, the others might be clear, right? This is the differential version of that, you can see, and these are basically, or this is how these things relate to each other. You understand the point now? Okay. All right, guys. Now, again, this is the Ito integral that is involved here. Keep that in mind. Okay, so whenever you're applying it, this is basically the Ito integral that we talked about in the last two sessions. All right, and this is a Riemann integral, by the way. Okay, the stochastic version of a Riemann integral. That will not disappear either. Okay, I'm going to show you some examples based on that, so you see basically how it's applied. Let me just do it. The first example that I'm going to use is, let's say, the function that I'm going to take. It has two derivatives. Again, you can differentiate it as many times as you like, but before I prove the statement, 1/2 times the argument squared, right? And then this implies that the first derivative is going to be 2 times 1/2 times x, which is the argument, which is simply just the argument itself, and which is the identity, of course, and the second derivative is going to be equal to 1, right? Because the derivative of x with respect to x is going to be equal to 1. So those are the things that you need. I suggest basically when Ito's lemma comes, and it will come, that you will basically just make sure what the derivatives are that are needed, okay? So then, of course, you will simply just need to apply it, okay? And the question is how? Now, basically, I'm going to apply it on the differential of 1/2 times the square of the Wiener process. And why I was doing that, because basically you might remember this, because that was one part of the Ito integral of the Wiener process. I'm not sure if you remember this. 1/2 times the square of the Wiener process minus 1/2 times t was the Ito integral of the Wiener process. You might remember this. Okay, so if you're not sure what I'm talking about, the Ito integral of the Wiener process, okay, I'm going to write it down like this, has been, and this has been also shown, you don't need to write it down, this is 1/2 times the square of the Wiener process minus t halves. All right, so that's basically what the statement was. I think I was showing that as well. Okay, that was also, took also a little effort to basically to confirm this. Okay, so this is part of the basically the Ito or result of the Ito integral of the Wiener process. So that's why I decided to basically to create an example to it, and that is a differential version basically of that. So you can clearly see what it's going to be now, because then you would need to address the differential version of that. Okay, so then you have the actually this part, and then you have the differential of that, 1/2 time basically of the differential of time. This is what it's going to be. You see, plus, not minus, plus. So mind that basically. Okay, I will come back to it. So this is just basically confirming the Ito integral again, because this is just, you know, circumventing it. Anyways, okay, so now basically the first expression is actually the first derivative of the Wiener process, sorry, the first derivative of the function f at point of the Wiener process, which is the identity, so that's just simply going to be the Wiener process itself. And then you have the differential of the Wiener process again, which comes back as I was mentioning it, and then plus 1/2 times the second derivative of the basically at the point of the Wiener process, which is equal to 1. Okay, so you see that's a second derivative, which is equal to 1, and then you have dt, and that's it. Okay, so I'm just incrementing it all the time because I was establishing this result already. Okay, I'm going to write it down again and then make the integral version of it. Okay, so then you'll see basically what it will be. Okay, because this is how it goes. And I was addressing this already. So here it is. Okay, here it basically would come. And yeah, so, but need to understand here, this is the Ito integral as I mentioned before. Okay, and that is equal, I mean, you saw that this is equal to t, right? Because the antiderivative of 1 is equal to s with respect to s, and that goes from 0 to t, so t minus 0 is going to be t then. You see? So this is just the way that I predicted. Actually, we were just circumventing it. Again, so basically to illustrate inconsistency, and that's why I was using that as an example, because this is something that you're already familiar with. So even if you were not sure what Ito lemma is, you already know what the Ito integral was, and what I introduced you to is a differential notation of the integral, and that's it. So this is the differential notation of the expression below, which is its integral notation. Both are not the same, but equivalent, because one is known, the other is known as well. Is this clear now, guys? Again, I'm doing the same thing all the time. I'm not sure you can grasp it. Okay, now we're gonna prove that. Again, and the proof is a little bit more difficult. I cannot do Taylor series expansion, at least not to the fullest, because I only have the guarantee that the derivatives, or only the second derivative, it might exist, but the third derivative might even not exist. You understand the point? So I have to cut off the Taylor series expansion, and I'm left with the remainder, for which I would need to develop some restrictions. So that's why it's going to be a little bit more difficult to prove. The first one is easy, right? Actually, relatively speaking, because all you need to have is a Taylor series and the quadratic variation of the Wiener process. But the second one, if basically not all derivatives exist, the function can be differentiated twice, but maybe not 3 times or so, then I need to basically stop the Taylor series expansion, and I need to take care of the remainder. Okay? So first off, again, then I would need to apply the Taylor's theorem regarding the remainder. Again, so which starts basically, I mean, this is already familiar, all right? So these are the same expressions that you saw, and I'm not going to basically elaborate on this. But what's the difference between the Taylor series expansion and the Taylor's theorem? The Taylor's theorem is making a statement about the remainder. If you basically stop the Taylor series expansion, because that would be you were not regarding the limit, you would need to basically look at the remainder. I cannot do it because, again, I only have the guarantee that the function can be differentiated twice, but not even 3 times, okay? Which includes larger classes, but the price that I pay is that the proof is going to be not difficult, but it's a little bit more difficult than the previous one. Okay, here I got the first derivative at point of the Wiener process, which is taken at the lower end point, divided by the factorial of 1 times basically the, you can call it the absolute variation of the Wiener process, okay, so or the length here of the process within that time horizon, within the ith subinterval, if you like. I have the second derivative, okay, but I'm not having the third. Okay, so again, I will stop it here. I will have the second derivative, but not the third. But since I cannot make any statement about the third derivative, I had to stop the expansion here. That's the remainder from the Taylor series. And I want to need to make a statement about that. Okay, now the statement is basically based on Taylor's theorem, is the following. Okay, the remainder is going to be finite, let's say, and there exists actually a constant between 0 and 1, for which you can basically express the remainder. Again, so why 1? Because after the first derivative it was interrupted, and that's the term, that's the issue. Okay, so when you interrupt this, and you might ask why not basically interrupting it at the second derivative if the function is differentiated twice, and the answer is because that would need to make a statement about the third derivative, which is expressed by the remainder, so I'm not basically supposed to do this. I will only basically stop it here. The statement that basically Taylor's theorem is making, again, there is lots of versions regarding the remainder of the Taylor's theorem, is that it can be expressed by the second derivative. And that's the reason why I was basically stopping it already here. Okay, after the first. Regarding the existence of a constant, by the way, so when you calculate, and this is what I'm going to do, inside, and mind that please, inside that parentheses, so which again is addressing the argument of the second derivative, and the second derivative has to exist because the function is at least supposedly be differentiable at least twice. Okay, now I'm going to make a so-called combination of the lower and the upper endpoints regarding the argument, and that is going to be the convex combination. So first I'm going to start by 1 minus alpha. Again, alpha is a constant between 0 and 1, which again, based on the Taylor's theorem, it must exist. Otherwise, you could not express it. So then you have a convex combination of the lower endpoint, or so let's say the Wiener process at the lower endpoint of the ith subinterval, and then the upper endpoint of that subinterval, the Wiener process at the upper endpoint of the subinterval. This inside, okay, inside basically, so that parentheses, which is again addressing the argument of the second derivative, is going to be a so-called convex combination of the lower and the upper endpoint, or sorry, the Wiener process at lower endpoint and the Wiener process of the upper endpoint. And Taylor's theorem claims that this exists. There is a possibility for that. And then dividing it by the factorial of 2 as you would continue. And then you have, let's say, the quadratic variation within that interval of the Wiener process. You understand the statement now? Okay, so that's basically the issue. And that's Taylor's theorem. So it can be written like this. So instead of using basically the upper and the lower endpoint, I'm simply using just a combination of the two regarding the Wiener process, and Taylor's theorem allows me to do it. Okay, so that's the issue. Simply there is some sort of a linearity here regarding it. Yes, and that's it. Okay, so now I'm going to basically play with that a little bit. First off, I'm going to take that to the other side of the equation, addressing basically the increments. And then, okay, I will just, rearrange that stuff. Here I got the remainder, which is here. So I'm going to write those down, which I do. Okay, and I basically keeping that, so just writing that down. Okay, here, this is basically clearing it up. And then I'm going to address the limit of those things. So you can basically create the sum, and then, the limits basically in terms of integrals, which you were kind of used to. Okay, so that's what I did here at least at this part. Okay, because here I was using the sums. In the previous part, I didn't. Okay, I was not using sums. I was using differentials, or increments, you can say. Okay, but increments don't converge. I mean, they do converge to 0, right? But that's not basically in that sense. It's not an abstract sense in that regard. Okay, these things converge. Now, this is going to be the increment of the function of the Wiener process. Okay, here it is basically at time point 0 is the Wiener process is 0 almost surely, but I keep it as is. Now, what about that? That will converge to an integral. And that is going to be basically the Ito integral. You see, the generalized Ito integral to which it converges to. Okay, in mean square, of course, right? Or the limit of that, which again is here. Okay, so that is basically the statement that I made last time. And yeah, and what about that? Now, that will also converge because here I just have a convex combination between the two, as if I was using some SI asterisks basically, because there is a time point at which they do actually equate to that combination. So that is linear. And that will converge to the corresponding Riemann integral of the Wiener process itself. Why the Riemann integral? Because the quadratic variation of the Wiener process is finite. Okay, so then you can basically make those statements here. And that's it. Okay, so now you see that also works due to the fact that this thing actually in particular, but I'm looking at that one, this exists, so alpha exists, which can be basically addressed like this. And yeah, so then I was writing Ito's lemma here in its integral part, or integral version, right? So that's the integral version of Ito's lemma. And then you can also write it like the differential version, right? So you can simply just basically write it down as the differential version. You can simply just skip the integrals and then, you know, write it. And I mean, of course, with time point t. You don't need to illustrate that this is an Ito differential from the Ito integral, right? Okay, which would be the case. It would be more practical, to be honest, but I'm not going to. So this is going to be 1/2 times the second derivative at the Wiener process at time point t, because again, I was expressing it as a differential, and then you have the differential of time, or the increments of time, infinitely small increments of time, and that's it. Okay, so now I basically was using it the other way around, so to have a little bit more flexibility in that regard. Of course, you don't need to learn these proofs, so you will not need to apply Taylor series expansion or Taylor's theorem or so on, whatnot. So this is something you will not need to do, but it basically would help. Anyway, okay, so we basically look at that definition, and then maybe we take a break after all. Diffusion processes are also functions of Wiener processes in this case. Okay, so I'm going to, based on the whole thing on the Wiener process, which is supposedly be there. And I'm going to create another stochastic process, which is basically going to be a function of the Wiener process. And that is going to be a so-called diffusion, or diffusion process, if it can be written like this. And I'm going to express it basically by its differential. So x is going to be a diffusion, basically, and this is expressed by its infinitely small increments at time point t, as you see. Okay, I mean, I'm not using integrals, but if you take the integral of that, this is going to be, again, so from, it really matters from which you would calculate, but if you change it to basically to s, then this is going to be x at time point t minus x at time point 0, right? But I'm going to express it in terms of its differential. So you have a, not the constant, but a function, okay, which is a two-dimensional function now. It depends on time. And it depends on the process itself. So it depends on two things, okay? And if you have something like this, this is called the drift function, by the way. The drift function is a function basically that assigns elements of a Cartesian product of the time component in the set of real numbers. Again, so the first argument is referring to time, and the second argument is basically going to be a process. This is just a deterministic function. It's not a stochastic form. It's a deterministic function. Okay? And you have real numbers coming out, so this is basically just going to be the case. And then, of course, you have the volatility function. This is how it's referred to, sigma. is also going to be a function of the same kind. It's not the same function, but it's going to be the same kind in the sense that it has the same arguments, right? But you have different results coming out. And that's called actually the diffusion function, okay? But you will need to know this. And then you have basically the differential of the Wiener process attached to it. If you look at the integral version, you can also basically address it too, okay? If I recall it correctly, I was also giving you that one. The geometric Brownian motion is one example. Other examples include, for example, the Ornstein-Uhlenbeck process, but I'm going to come back to that later on. Now, the integral version, again, is equivalent to the differential version, but it looks like this. So you have basically the process at time point t minus at time point 0 being equal to the integral from 0 to t of the differential of the diffusion function, right? Where basically, with respect to it. So you would need to basically integrate that with respect to time, you see, okay? This is just a one-dimensional integral, although you have basically two arguments for the function, and then you have basically the other expression, which is a stitchless integral, as you see. Basically, you have some sort of a Wiener process here as the increments. All right, okay, so that's basically the diffusion process. You're going to see some examples, and I'm going to show you how to apply Ito's lemma on the diffusion process, because that's going to be the next part, okay? One example of the diffusion process is the standard Ornstein-Uhlenbeck process. The Ornstein-Uhlenbeck process is going to be a stochastic process which looks like this, okay? So it's going to be a function of a Wiener process. Now, since you have seen this, I'm going to express them in terms of their differential, because it's a little bit more difficult to express them in terms of their integral version. Okay, so when you have a process like this, okay, so you have c times the process at time point t, where you have dt, which is a differential, and then you have basically the increments of the Wiener process in terms of their differential. Okay. The issue is this: it's not straightforward to basically to solve this for, that's going to be the subject of next lecture, is how to solve those things. Sometimes it can be solved directly, which we're addressing, but here it's not directly solvable. Again, it is solvable, and I'm going to teach you how to, but not directly. So you simply you cannot say, okay, I'm going to integrate this thing. Because the question is, okay, what is going to be the integral of that then? Okay, but again, you'll see how this works. Anyways, but you can do Ito's lemma based on that. Okay, so you need to understand what the drift and the volatility functions are. Okay, in this case, the drift function is simply just a linear function. It doesn't depend on time anyway, so you can not, at least not directly, so you can basically skip that one. But in the general case, it's a two-dimensional function. Here it's just a one-dimensional function degenerating to it. And the volatility function is the same. It's actually not even basically a function. It's a constant, right? Because it's equal to 1. So this is how it relates to it, you see? So if, again, basically the drift function is like this and the volatility or diffusion function is like this, then you can simply just say, okay, the Ornstein-Uhlenbeck process is an example which is basically expressed by the diffusion, okay? Most processes are, okay? So the processes that you're considering are going to be diffusions. Another one is the general version, which I'm going to address also. The general version incorporates a linearity for the drift. So you're not just basically having a constant, which is proportionate, but you have basically a linear function as a drift function, and the volatility can be basically so anything as long as it's constant. Again, regarding the increments, okay? So that is basically the issue of the process. Okay, now you need to change the drift and the diffusion functions accordingly because they'll no longer fit. And regarding the diffusion function, it is, as an example, that is also a diffusion process. Later you're going to see the geometric Brownian motion, which is also a diffusion process. All right, so we are going to continue, and we are going to look at another example, which is, as I mentioned this before, the geometric Brownian motion. Now, the geometric Brownian motion is also a diffusion process, and that is actually characterized as follows. It looks like this. So you have a constant times the value of the process itself, whereas basically you have a differential here for time, and then you have sigma times the process, and that is also including the differential of the Wiener process. Now, in this case, as you see, the drift function is a constant times actually the stochastic process. Is not directly depending on time, so it's not explicit in this regard. And then the diffusion function is also kind of similar regarding linearity here of the function. Now again, I'm going to teach you later on how to find the solution of it, okay? But you can basically just take that with a grain of salt, because we're going to look at, regarding Ito's lemma, we're going to look at the increments of its logarithm, okay? So that is basically what it's what we're going to do. You're going to see this later on. It's edited a little bit more appropriately. Okay, now again, the quadratic variations of the Wiener process, and we have basically talking about this before, so I don't want to waste your time anymore on that. Have already been addressed, but I want to basically create a transition to the quadratic variation of diffusion processes. Okay, so again, when it comes to the Wiener process, based on the quadratic variation of the Wiener process was finite. Actually, that was converging in mean square to t. That was it, okay, which I expressed in terms of an integral. So as the number of subintervals increase, that was it. Okay, so this is just, you know, the symbolic notation. And of course, we're going to look at diffusions now. So this time we are basically addressing the quadratic variation of diffusions. And again, x is the Wiener process, x is the diffusion, and it is driven by the Wiener process W. Okay, so the diffusion is looking like this. Again, here is the drift function, and here is the volatility function. You saw that before. And now, again, I'll slow down a little bit, because now I'm going to address the quadratic variation of it, okay? And not the quadratic variation of the Wiener process that you basically just seeing right now. This is actually basically, I mean, when you would complete it this far, that would be actually the limit of that. Anyways, we've done this before. Okay, now what I'm going to do now is I'm going to replace the Wiener process by the diffusion. And that is going to be basically the quadratic variation of the diffusion. And that's it. Okay? Now, what you are supposed to do is this. Okay, so when you look at that, you just need to look, I mean, when it comes to this part, okay, so this part, the quadratic variation of that is supposedly be 0. Because when you address this differential, or the square of that differential, that is going to be 0. So the drift function will not play a major role regarding the quadratic variation of the process. However, the square of that differential is equal to the differential of time. And that's not going away. Okay, so what you have is the square of the drift function, diffusion function, basically, okay, multiplied by, I mean, multiplied, I put in quotation marks because there is no multiplication involved, multiplied by the actually the square of time. And then of course you have basically a function on which the diffusion is also applied, and that can be also incorporated into the integral. Okay, so again, let me repeat, SI asterisk is somewhere between S at the lower endpoint and the upper endpoint of the subinterval. And let's say the function is a real valued function which is continuous. Okay, so the question is, when does that occur, when does that basically limit is going to be finite, but I'm going to address this later on. Okay, so first I'm going to basically address the diffusion. So you have the function at that point, okay, at point xs, and then what happens to that is basically can be seen here when you square those. Okay, so when you square those, you get the square of the diffusion function, which I'm not going to write it down, and then you have dt, and that's it. Okay, so then you can simply just basically replace it by it, because that is corresponding to it. If you're not sure why, I'm going to basically explain this later on. Okay, so now you have the square of the diffusion function, and the quadratic variation of the Wiener process becomes basically, can be associated with time. So you have the differential with respect to time, and that's pretty much it. So the question is, when does this happen? And it is happening if, and only if, actually, the function is continuous, almost everywhere at least. Okay, and then so thus this integral will exist and will not be basically an issue. Now here is the key. Okay, so here this part, again, when you express it in terms of differentials, would converge to the square of the increments, right? Here, which you see here. So when you would look at the square, now when it comes to that, this part is going to be only interesting, so the square of that, because here this variation is going to be actually 0, and so is basically 2 times that, so that is basically the another thing. And if you want to take basically the square of that differential, this is going to be the square of the diffusion function, and then attached to the square of the differential of the Wiener process, which is actually corresponding to time. Okay, so that's the reason why, basically, where you would have it. Okay, so from intuition, I think, again, I don't want to say too much. I have to admit it looks horrible. Okay, but when you break it down into basically to its point, you find it's not that big of a deal. Okay, the only thing that is interesting here is, again, the quadratic variation of the Wiener process, because that will be basically associated with time, and that's it. Okay, and anything else will be disappearing. Okay. Yes, and this is how quadratic variations of diffusion processes can be computed. Okay, and this is basically the final, or the limit of the quadratic variation, actually. Okay, I'm going to take that and make the next theorem based on around that, and that is going to be Ito's lemma on diffusion processes. Okay, so that is going to be basically the fundamental. The previous statement was actually the fundamental theorem based on that, and now it's becoming relatively easy. So how would you basically apply this? And I'm going to do it. Okay, so for diffusion processes, so you have actually a continuously twice differentiable function on which basically is applied almost surely. Okay, and you have basically a Wiener process that is the driving factor of the diffusion. Okay, so X is basically the diffusion. It is driven by the Wiener process here. Okay, so that's the reason why I was basically keeping the diffusion equation here down below. And the question is, how is Ito's lemma applied? And we're going to basically practice that one. So just for a moment, you'll see this later on. So the differential of the function of the diffusion. So you have basically looking at not the increments of the diffusion, but the increments of the function of the diffusion, is going to be the following. So first off, you have the derivative of the function at the diffusion, okay, where it's basically you'll attach to it the differential of the diffusion, which is corresponding to the increments of the diffusion, by the way, so you'll see this later on. You can treat them as factors, those differentials. This is just a pseudo multiplication, so there is no multiplication sign here involved. I will not freak out in the exam when I see this, but that's basically how it will be. And then you have 1 by 2 times the second derivative at the process, okay, so you put it basically a process at time point t, times the square of the diffusion function. And then, of course, this is also, that is basically referring to time point t. I was addressing this issue basically based on the integral version of the previous section. So this has been addressed. Okay, that is a square, actually, or the quadratic variation, basically, of the diffusion. And this is corresponding to another stochastic integral, which can be also an E2 integral, by the way. So you see that how it's applied. Its integral form is simple, so I'm not going to basically waste on time on that because most of the time it's expressed by its differential version, and I'm going to show you how to apply it. It's a step-by-step, but if you take the integral version of that, here it is. Again, I was explaining it prior. Okay, what is true for the Wiener process is also going to be true for the diffusion. And then you simply just write down the integral for those differentials. You can change basically the time component here. The reason why I was basically addressing it, this part, is that it can be neat integral, by the way. Okay, so it's usually it is actually because it has basically the Wiener process in it. But that's basically the expression, and then you have this expression, which is the differential version of the upcoming expression that you're about to see. Okay, so you simply just, I supposed to, okay, I made a mistake here, I just see it. I supposed to call it S because S is supposed to be the integrator here. Okay, so it's not consistent with that in this regard. Here I was doing it correctly in this part, but here for the others I wasn't, so I will need to fix that part. Okay, I'm going to change that. So I'm going to update the slides after that. Okay, it's not a big error, but it's not consistent. Again, you're not supposed to basically call the integrator as well as the upper endpoint of the integral the same. Okay, you're supposed to call it differently. Anyways, okay, I apologize for that, but you're going to see basically, I mean, the differential version more often. Anyway, now we're going to apply that on the geometric Brownian motion first. Okay, and then after that, I'm going to make a generalization, and then I'm going to apply it on the Ornstein-Uhlenbeck process. The geometric Brownian motion that you already saw is looking like this. So that is basically the geometric Brownian motion, right? And the question is, how would you basically apply Ito's lemma on the geometric Brownian motion? Again, this is the formula, and that's going to come. Okay, so that's basically one of your assignments. Okay, and so we're going to practice it now. I want to basically look at the increments of the logarithm. The application of the increments of the logarithm is that you analyze basically the evolution or the dynamics of the returns of the asset. Okay, so if the asset follows a specific stochastic process, the increments of its logarithm is equal to its returns. Because if you look at basically, let's say ST is a current stock price, ST minus ST minus 1 divided by ST minus 1 is basically the return. Okay, on the stock. So the current observation minus the previous observation divided by the previous observation. And this is approximately the increments of the logarithm of the process. Okay, so when basically the time horizon, the time change is small, that equation becomes actually reality. That's why basically it's called the log returns. Okay, so the log returns are based on that. Log returns are the increments of the logarithms. And when you look at daily returns, it can be basically associated by that. So that's the reason why I basically would like to know how to calculate basically the increments of the logarithm, because the increments of the logarithm, you can basically associate that with returns. And returns are relative price changes. So if xt is basically the price of an asset, okay, and based on the Black-Scholes model, the Black-Scholes model assumes that actually the stock price follows the geometric Brownian motion, but that's just another side of the story. How would you calculate basically the increments of that? Or how would you basically, assign the return process? Anyways, and Ito's lemma is going to basically answer that question. Now, first off, I need to have the function that is involved, which is the logarithm, right? The natural logarithm. Then, I would need to differentiate it. The derivative of a logarithm, if basically the logarithm, if differentiated with respect to x, ln of x is going to become 1 by x, and 1 by x can be rewritten as x to the power of minus 1. I was just basically writing it like this, but this is just, that had to do something with editing, so x to the power of minus 1 is going to be the derivative of the logarithm. I think everybody knows this. And the second derivative is going to be, if you differentiate x to the power of negative 1, it's going to be negative 1 times x to the power of negative 2, which is actually negative 1 by x squared. Okay, so that's going to be the second derivative. And those are the derivatives that you need. So again, let me remind you, this is negative 1 by x squared, right? Okay, so those are the derivatives that are involved. Anyway, now first off, I will need to have basically the derivative and, the derivative of the function on which basically the differential is applied. So the derivative of the logarithm is 1 by x if you differentiate it with respect to x. So this becomes, if you need to put in x, the process itself, this is going to be 1 by the process, of course, right? So that's it, you see? And then, of course, you have basically, the increments of the process, or which supposedly be infinitely small, and then minus, because here it comes, this is going to be minus 1 by x squared, which is minus 1 times the process, but here we have 1/2, so minus 1/2 times 1 by the square of the process, which is here, according to it, okay? And then you have the square of the diffusion. Now, this is the diffusion, okay? Its square is going to be sigma squared times the square of the process, you see? So this is actually the square of this expression, because that's what you have here, you see? So you need to square it. Okay, so sigma is becoming sigma squared and x becoming x squared, of course. And then basically, actually the square of that, which is the differential of time, right? I was basically explaining it because the quadratic variation of the Wiener process is finite. Okay, so that's the reason why this term will not disappear. Now, and then you can clean it up, of course. Okay, so if you clean this up, which I do, okay, because 1 by x squared times x squared is going to be 1, after all. And after that, I'm going to substitute basically by the differential here, which is this equation. So I'm going to substitute that, okay, to put it out here. That's it. Okay, so that's what I did. And later on, you can basically cancel 1 by x, or basically you can cancel x, because 1 by x times x is going to disappear as well, okay, from those parts. Okay, and that's basically what you're left with, because here in this part, I'm going to take that and squeeze that into that expression where the differential of time is, and then you're done. Okay, so then you're done. And this equation, or this stochastic partial differential equation, can be solved relatively easily, and that's the issue. Okay, so next time I'm going to start from here, and then we're going to solve this. Okay, so what I mean by solving it, I want to know basically what xt is. That's it. Okay, and then, but that's not going to be that difficult. You'll see that later on. Okay, so that's one example for Ito's lemma, and again, there is a large variety of applications, especially in finance. I'm going to basically talk about that later. Now, okay, well, see, okay, regarding the proof, the proof of that is having the same structure as the previous one. So I'm not going to prove that directly, because again, this is just wasting the time. It has, all I'm doing in this case, and that's what you see, okay, is based on the Taylor series expansion. I was, cutting it off. All I'm doing is actually just replacing the Wiener process that you saw by the diffusion. So when it comes to basically the proof of the diffusion, all I was basically doing is replacing the Wiener process by it, the diffusion by it. And that's it. So again, I'm not going to waste your time, but it has the same structure. So those expressions might be basically, you might be familiar with. Okay, and then of course you have the second part, which again, based on Taylor's theorem, with the complex combination, you might remember that 1 minus alpha times the diffusion at the lower endpoint of the ith subinterval, and then plus alpha times the diffusion at the upper endpoint of the ith subinterval by basically the factorial of 2, which is 1/2 in total, okay, as a factor. And then you have basically the quadratic variation of the diffusion within that subinterval, okay? And those things converge. Okay, so that's basically the issue regarding the Taylor's theorem. You will not need this for the exam, but I'm doing it right now for the 3rd time. And all I'm doing is basically just replacing the expressions that you saw in your previous case. I was taking more time for that, but here you don't need that. This is the integral version. It doesn't actually converge anymore, because you'll sum up the increments, which is not going to be the case. Now here in this case, this converges to an integral, which can be an E2 integral, by the way, mean square. Okay, and the expression is, of course, the derivative, there is an RMS error here, which is the derivative of a function, which is missing. Okay, so I'm going to need to fix that one as well. Okay, so here it is. I apologize, this is basically including the derivative, but in the final statement, it was written down correctly. And regarding that, again, this converges in mean square, as we see basically prior, when it comes to the quadratic variation of the diffusion, and the limit is going to be 1/2 times the integral here from 0 to t of the second derivative. So here's the first derivative, which is missing. Again, I apologize for that, and here is the second one. And up to the, basically the third one will no longer converge. Okay, or it will converge, but it will converge in mean square to 0, by the way. Anyways, yeah, so again here, and I recognize that here there is, again, too many variables. The integrator is supposed to be called S and not T. But anyway, all right, so that's the issue. Here it's correct, but here it's not. I apologize for these inconsistencies. Anyways, okay, so that's basically it. I was not summarizing it, but that's just identical to the previous statement regarding functions of Wiener processes. So that was the third type. And now we're going to look at the basically for two diffusions, so multiple ones. When it comes to two diffusions, you need to have the partial derivatives. I'm not sure if you know what partial derivatives are regarding functions that depend on basically, multiple variables. For example, x and y. So for example, when you have x squared times y cubed or something, and then you look at the partial derivative of x, which is going to be 2x times y cubed, and then a partial derivative of the function with respect to y, which is, in this case, 3 times x squared times y squared, right? Okay, so you might remember that, okay? And in this case, this can be extended, okay, to multi-dimensional diffusions, if you like, okay? Whereas basically what I'm going to do now, so let's say you have a continuously twice-differentiable function almost everywhere with respect to both arguments, by the way. Okay, so not just basically one, but with respect to both arguments, which is not on the slide, but it's not that big of a deal. It will be. So the functions that you're going to get are going to satisfy these things. Otherwise, you would not be able to apply Ito's lemma on them, actually. Okay, and there is going to be two diffusions now, but they have something in common, which is the common Wiener process. Each of them are going to be driven by the same Wiener process. Okay, so that is going to be the same Wiener process, which is actually the commonality that they have. So I was writing down both basically diffusions in terms of their differentials. Okay, so at the basically up you see the first and then you see the second. Okay, so just basically writing it down, but I need to distinguish between the two. So mu1 is a diffusion function of the first diffusion, and mu2 is going to be the diffusion function of the second diffusion. Okay, so they have the identical structures. All I'm doing is basically indexing them. Okay, so you have just the same structure here for both. Both are diffusion processes. One can be a geometric Brownian motion, and the other can be an Ornstein-Uhlenbeck process, each driven by the same Wiener process. So that's the commonality that they have, is that they have basically the same driving factor, but maybe a different specification, different functions on the same Wiener process. In this case, you can basically generalize Ito's lemma, as I do, okay? This is going to become weird. Okay, so I'll probably take this off, okay, from the exam because it has a lots of, let's say, lousy expressions in them. But don't be scared. Okay, so the first is, this is the notation here for the derivative. I'm not sure if you remember that. Del means that you're differentiating a function. Which one? You need to differentiate f with respect to, check this out, with respect to x1. Okay, so that's basically the first derivative of the process with respect to x1. It's not that big of a deal. It looks horrible, I have to admit, but It's not that big of a deal. Then you attach the dynamics of the first diffusion to it, and then you do the same thing basically for the second. So the first derivative of the function with respect to the second diffusion, and then you attach basically the dynamics of the second diffusion basically to it. Okay, so that's not that bad, to be honest. Okay, so this is the total differential, by the way. I'm not sure if you know that term. Okay, so when you have deterministic functions, this is the total differential. So you differentiate the function with respect to x, all right? And then you have to differentiate the function with respect to y, for example. You might be familiar with those things. Okay, so that's what you see actually. Now here comes the thing. When it comes to Ito's lemma, I mean, the total differential will stop here. Actually, it would continue, because if it continue, you have the second derivatives, right? So you would have 1/2 basically times the second derivative with respect to x, actually where you have the square of that differential, but that's going to be 0, all right? Or the corresponding integral is going to be 0, because the quadratic variation of the identity is actually, as we saw, 0. So those differentials are going to be canceled, but not in terms of a Wiener process, because the quadratic variation of a Wiener process is going to be finite. All right? It's not 0. I mean, 0 is also finite. But anyways, okay, so you have 1/2. Now check this out. Don't be scared. This is the second derivative of the function f with respect to basically where you differentiate with respect to x1 2 times. So you're differentiating with respect to x1 twice in a row. You understand that statement now? Okay, so this expression, this is multiplied by the square of the first diffusion. Okay? And then you multiply, you do the same thing for the second diffusion as well. So you have 1/2 times the second derivative with respect to the second diffusion, okay, times the square of the second diffusion function, right? Which is you can call it the volatility function. So that's it. And then, of course, you have you can call it the cross derivative, is how I basically call it correctly. So you have that also twice. So 2 times 1/2 yields basically 1. So you have the second derivative where you differentiate with respect to x, and then you differentiate with respect to, with x1, and then you differentiate with respect to the other. Now you can change the order of differentiation, right? You might know that the order of differentiation is not relevant, so you can also differentiate with respect to the second for the first one, and then with respect to the third. And that's basically it. And then you have the 2 diffusion functions, which are multiplied by each other, attached to the differential of time. Okay? Guys, I have to admit it looks horrible, but it's not that bad. Okay? So here, you're probably familiar with that. This is the total differential. And since basically the quadratic variation of the Wiener process is finite, not 0, you have basically some expressions regarding the second derivatives included into that expression also. Okay? I'm going to apply this, so I'm going to make an example to it, and that is going to be addressing the stochastic product rule. You might remember the product rule of differentiation, whereas the derivative of a product is not the product of the derivatives. So this is going to be basically the u prime times v, right? And that's basically the issue, plus u times v prime in the standard case. If you want to express this in terms of the differential version of it, okay, so I'm going to basically do the same thing, as you can see. Okay, I'm going to do it now, so you see basically how it's done. So this is going to be u prime attached to the differential of v, see? Okay, and then plus you have, yeah, you can do it like this. And then you have v prime attached to the differential of u. That's it, okay? I was changing the order, and that's the differential version of that. Because if you integrate this, okay, so check it out, if you integrate that basically on both sides, you get this back. All right, so that's basically how it is. You understand the point now? Okay, so I'm basically addressing the derivative of that here. I forgot to denote this. This is the the differential of the derivative, which is the original function, by the way. So this is the original function. So here is basically this integral version is going to be the original function again. You understand this notation now? So this is not going to be big of a deal if you're used to the differential notation. So you can express these basically in terms of differentials. Okay, so first off, again, if you have basically two arguments, x1 and x2, you take the basically x1 attached to the basically, I mean, you can, okay, so that's basically, okay, this is the function that you would try to differentiate. And now, before I apply Ito's lemma on it, I'm going to calculate the first derivative of the function with respect to x1. So what is going to be the derivative of that with respect to x1? x2 is a constant then, so it's going to be x2 after all. Okay, so in this case, then I'm going to address the first derivative of the function with respect to x2, which is x1 now, because in this case, if you differentiate that with respect to x2 now, then x1 is going to be the constant. Okay, so those are things that you should basically be aware of. Then I'm going to address the second derivative of the function with respect to x1 2 times in a row. So basically you do it basically 2 times in a row after all. So let's differentiate that with respect to x1. Now it doesn't depend on it, so it's going to be 0, okay, because it's a constant. Then I'm going to differentiate basically this function with respect to x2 again, because you were differentiating the function f twice. Okay, with respect to x2 in a row. It doesn't include x2, so it doesn't depend on it. So its derivative is going to be 0 after all. And then you look at basically the cross derivative, whereas you would either choose to differentiate this function with respect to x2, which is going to be equal to 1, or this function with respect to x1, which is also going to be equal to 1. So whatever you do is basically, if you change the order of differentiation, it doesn't really matter. That is also going to be equal to 1. By the way, so that's it. And then, of course, okay, if you go back, so the statement that I was making regarding Ito's lemma for 2 diffusions, which you're about to see again. So this is basically the previous statement that I was making. Again, I have to admit it looks horrible, okay, but it's not that bad, okay. First off, you have basically, I mean, we were expressing those things, so don't worry, I was collecting them. This expression was 0. I mean, why? Because the second derivative here was 0. Okay, so I'm going to take that out. And that expression was also 0. Why? Because the second derivative is 0. Right? So I'm going to take that out as well. So these things are taken out now. This expression was equal to x2, if recall it correctly, yes. And that expression was equal to x1. So I'm basically putting those together. And the cross derivative was equal to 1. And then, of course, you can skip that, because 1 times something which is, okay, is just that. Okay, and that's it. Okay, so that's basically it. This is the stochastic version. Again, this is the deterministic version. And then comes a stochastic version to it in terms of the differential. And if you have diffusions which are driven by the same Wiener process, this is basically what it's going to be. Does that make sense, guys? Again, so the first part is the deterministic one, which you might be not used to, but that's a differential version, basically, of the product rule. Okay, so just you can integrate the function, and you can see that basically later on. And then comes basically a stochastic component into it, due to the fact that the quadratic variation of the Wiener process is not 0. Okay, that's the issue. Okay, so these things appear because of the Wiener process, or because of the process, the properties that the Wiener process has. Based on that, I could also address the quotient rule. Okay, you remember the quotient rule? I'm not sure if you do. Okay, but from school or wherever. So when you have basically a quotient of 2 functions, this is going to be u prime times v minus u times v prime divided by v squared, right? Remember that? I'm not sure, basically. Okay, so you can express that in terms of differentials if you like. So that's not a big of a deal. The only differentials that you need are going to be here. So here and that one, okay? But you should basically drop the multiplication sign, because it's not correct, and v squared can be kept. Okay, so that is a deterministic version. Well, the problem is that the stochastic version is going to be a little bit more complicated than this. Okay, I'm going to make the statement first. Okay, so this is basically here. Now, we want to calculate the derivatives. Okay, differentiating the function. First with respect to x1. If you differentiate with respect to x1, so you got x1 times a constant. And if you differentiate that, this becomes the constant times the derivative of x1, which is 1. So this is going to be 1 by x2 because that is the constant by which I was multiplying it with. Again, if you differentiate with respect to x1, then x2 is a constant, and so is 1 by x2 as well. If you differentiate with respect to x2, okay, so that's basically the notation here. So, I mean, I'm not sure if you know this, but what is the derivative of x to the power of minus 1, which is actually negative 1 times x to the power of minus 2 with respect to x, of course. And the reason why I was basically addressing it, because x to the power of minus 1 is 1 by x. And I got 1 by x2 in this case. So this is x1 times 1 by x2. In this case, since I'm differentiating with respect to x2, then, okay, I would need to find the derivative of that because, again, this is a constant now. So x1 times the derivative of 1 by x2, which is negative 1 times x to the power of negative 2, okay, which I'm going to rewrite. So it's going to be negative, right? You need to understand why, because the derivative of 1 by x with respect to x is negative 1 by x squared. That's the answer. So then you come negative x1, okay, times the derivative 1 by x squared, which is basically the derivative of the function f with respect to x2. All right, that's it. So again, it's not that bad. I have to admit it looks horrible because you have too many indices and whatnot, but you can basically just ignore those. So ignore the time components, ignore, those capital letters and so on, and just, differentiate those things as you're used to. Now I'm going to take the second derivative of that with respect to x1. It doesn't have x1 in it, so it's going to be 0. If you differentiate that with respect to x1 twice in a row, it's going to be 0, right? It doesn't depend on it, so it's not going to be there. And if you differentiate this derivative with respect to x1 at this time, x2 time, because we differentiate that 2 times in a row. Again, the question is, what is the derivative of 1 by x squared? The derivative of 1 by x squared is the derivative of x to the power of negative 2, and that is going to be negative 2 times 1 by x cubed, okay? So you have basically cubed there, okay? If you're differentiating that with respect to it. And then, of course, you have negative 1x, which is multiplied by it, so that yields 2 times x1 by x2 cubed. That's it. Okay, so that is what you're about to see. It's not difficult. Again, this is just, the horrible representation. But again, I'm addressing stochastic processes now. And then, of course, you have the cross derivative, which is also there. Okay, so this is basically how it looks. Now, for the cross derivative, you can basically differentiate that with respect to x2, for example, because you're already differentiating the previous one with respect to x1. So then you differentiate with respect to x1 and then with respect to x2. This is going to be negative 1 times 1 by x2 squared, right? So that's it, okay, because of the fact that the derivative of 1 by x with respect to x is going to be negative 1 by x squared. Here we go. So that's basically what it is, okay? Now, those are the components. And I'm going to take those and put that into Ito's lemma, and then you'll see what it's going to be. So here it comes again. I'm going to make that statement, that horrible, horrible statement. But again, after you're realizing it, these are just the indices that make them so horrible. Actually, it's not that bad. Okay, so it's not that bad as it appears. I have to admit it looks horrible, even to me. Okay, and I'm used to something. I can tell you, right? But it's not that big of a deal. I'm going to break it down by the things that we were calculating. Okay, the first thing that we're calculating is a second derivative of the function with respect to x2, which was 0. So I'm going to take that out. Okay, so that's going to disappear. Then next, that was, I'm not sure what it was, but that was 1 by x2. That was it. Yes. Okay. Again, I'm not sure whether I can recall them, all of them, but you have seen that on the previous part. This was including the sign, something negative. I remember that one. Yeah, x1 by x2 differentiated with respect to x2 is going to become negative x1 by x2 squared. Here it comes. Okay, that's it. Now, this was, again, the second derivative here with respect to x2, so you differentiated it twice. This was with the cubed expression, so that was 2 times x1 by x2 cubed, right? That was it. I remember, okay, here it was, and then of course you can cancel 1/2, so that's going to disappear, and after that you'll basically have the cross derivative. I'm not sure what it was, 1 by x1, 1 by x2 differentiated with respect to x2 was negative 1 by x2 squared. Yes, negative 1 by x2 squared. Here it comes. Okay, so that's it. And then, of course, okay, I did some editing, okay, now. And you find a common denominator. Okay, so for each expression here, the common denominator is x2 squared. And the common denominator here for those two expressions is going to be x2 cubed. Okay, so I will need to extend this a little bit. All right, that's what I'm going to do, and that's what I did. Okay, so here, basically in the previous part, here I did it. So basically to make them basically more accessible using the common denominators of each expression. Okay, so those two can be merged. Okay, which I did because now they have the common denominators. Okay, you see, so it's not that bad. x1 times the square of the second diffusion function. It's just the first, and minus x2 times x1 times, sigma 1 times sigma 2. Forget about the arguments and the indices, so it's not that bad. Divided by actually x2 cubed, all right? And what about that? You can merge that too, because already the common denominators have been achieved, which is x2 squared. So you have x2 minus x1 with the differentials, and then that's it. Okay, it's not that bad. Here, again, I was repeating myself. This is the differential version of the quotient rule, the deterministic one. And here it comes the stochastic component with it, due to the fact that the Wiener process has the quadratic variation, which is greater than 0. Okay, so that's always the answer to that fact. Again, so my job is basically to make those things a little bit more accessible. But when you realize, when you're familiar with the basics, it's not that bad. The only thing that makes those things horrible is the indices. Okay, maybe I was thinking about when I was editing it to skipping those. Okay, but then I would not be consistent regarding the notation, so I don't want to risk that. Okay, but just ignore these indices. You can ignore the indices in the exam, by the way, so I'm not going to be freaking out, but when you write a thesis or so, you're supposed to include them. Okay, because from a mathematical perspective, it's not very clean. Anyway, now I'm going to recall basically we did Ito's lemma for 2 diffusions again. So I was making that statement a lot of times. I'm going to make that finally again. So just basically for editing, I'm not going to comment this anymore because you saw this, let's say at least 3 times or so. So basically those were the things that you saw. Here are the diffusions. Okay, because I want to use a specific case where I replace the second diffusion by a deterministic function. So you're about to see that later on. I'm not going to expand this anymore. The second diffusion is going to be replaced by the deterministic function. Okay, but the statement goes like this. So you have basically the differential of, you can call it the total differential, basically, of the function f, whereas both stochastic processes are involved. Again, if basically you had deterministic components, that would be basically the total differential to it. Okay, so the derivative of the function with respect to the first argument actually attached to the differential of the first argument, plus the derivative of the function with respect to the second argument attached to the differential of the second argument. I don't say times, but this is not a multiplication, but you can refer to it as such. Again, if this is the total differential, by the way. Okay, so if x1 and x2 were deterministic, that would be it. That would be it. If that was basically deterministic issue, there is no quadratic variation anymore. All right. and they're, because, I mean, diffusions are 0, but it's not, okay? So you have basically the second derivatives as well, okay? I was making that statement already, so I'm not going to make it again, okay? But these are the things that are involved. So you have the squares of the diffusions, and yeah, that's it, all right? So you see these things after all, okay? All right, yeah, okay, see? And of course here I'm going to finalize that. Okay, so here is basically the final version. I was just basically editing it. And I'm going to look at a specific case again. So that's also the third corollary, because I'm going to address Ito's lemma when time is involved. So when basically the functions, the deterministic functions, depend on time. Here I'm talking about basically the drift as well as the diffusion functions depend on time, for which basically for the geometric Brownian motion they didn't. Okay, but again I'm talking about basically that function. All right, so with time, what does that mean? This means that basically the second process is a deterministic one. I was deciding it for the second process. So if just basically it's a deterministic one, the diffusion is 0. If the diffusion is 0, there is no Wiener process anymore. There is no increments, and it's a deterministic one. And it's not even basically considering anything else. Okay, so that's just the differential of time. Now, if this is happening, check it out. What happens basically to those things? Now, sigma 2 is 0. So anywhere where you see it, you're going to just simply just kick it out. Here and there. Okay, so those where you can get rid of them. Okay, you see? It's not a big issue. Now, as I see here, the differential of the second diffusion, which is not a diffusion anymore, right? It's basically just replaced by time. You see? So the diffusion is gone. It's not there, right? It's gone. You see? You should basically, okay, delete it over here. This is what it becomes. So you differentiate basically the function f with respect to time now. Maybe the function depends on time, okay, which will be for the Ornstein-Uhlenbeck process. Okay, and then of course I put away the indices of the diffusions because there was just one diffusion left. Okay, so the second was eliminated by time, and basically the first is just, you know, just there. So there is no indices anymore. I was deleting them. And then, yeah, so then of course, then what? This is it, actually. So then you just simply clean it up, and that's what you're left with. So those things are disappear, and that's a special case. The only issue, so when time is involved, the only thing that comes with it is this expression, right? Okay, that was missing. But other than that, it's just actually, I mean, I need to give you a hint why it's there. Okay, so I was starting basically by two diffusions where one was degenerating and the other is basically just there. Okay, but that's it. So this is the new expression that comes with it. Function depending on time. I'm going to give you an example so you see how it's done. Okay, so that is the general case. Okay, so and that is basically the most common one, especially in finance. So I'm going to take that and I'm going to apply it on the Ornstein-Uhlenbeck process. If you want to apply it on the Ornstein-Uhlenbeck process, so let me recall what it was. Here it is. So you have linearity for the drift, and then you have basically some sort of a constant diffusion, which is 1. Anyway, and I'm going to apply this on the differential of e to the power of negative c times t. Now you might ask yourself why, but this is, I mean, when you review finance, this is a discount factor. So what you're doing is basically you calculate the net present value in a continuous time framework of, let's say, of an asset. Okay, so if xt is, you know, that you know, some sort of asset price at time point t of asset x, okay, and then you multiply it by this discount factor, this is the present value of it. And I want to basically address the dynamics of the present value. You understand the point? So that's the application behind this. Again, so e to the power of negative c times t is a discount factor. Why? Because, again, This is the deterministic part of it. So then you, of course, if it was deterministic, so if the payoffs were known, which grow linearly, I mean, you would need to address basically how they evolve. Anyways, okay, so I'm addressing the present value. And I'm going to basically, in addition, I'm going to address the dynamics of the present value by this expression. Okay, so the differential here is addressing the dynamics of the present value. This is interesting, for example, when you look at, interest rate derivatives and all that stuff, bonds, whatever. Okay, so then you would, basically apply on that. Okay. The Ornstein-Uhlenbeck process is stationary one, by the way. But again, so that's not going to be something which I'm elaborating here. Okay, so then you know what the context might be. Anyways, I'm going to apply Ito's lemma here. And of course, I need to have the derivatives of the function that is involved. If you allow me, I will finish that. So I'm going to try to keep that in mind. Now, the function depends on time and on x. Okay, which is e to the power of negative c times t times x, which is here. Okay, so again, this is a discount factor calculating net present value of x. First, I'm going to differentiate with respect to t, for which I need to chain rule. The other derivative is the same. This is a constant. The other derivative is the same, which is e. I'm putting in the inner function into the outer derivative, and I'm multiplying it by the inner derivative. The inner derivative is negative c, because negative c times t with respect to t, if you differentiate that with respect to t, you're going to get negative c. So that's going to be the inner derivative of that. The derivative of the function with respect to x is easy. This is just a constant. After all, so constant times a function becomes a constant times the derivative of a function, which is equal to 1, so that's that. And fxx, which is here, so I don't need the others. Again, the others are thrown out because they are 0. Okay, there is no dynamics involved here for the others, so I need to differentiate with respect to x twice and with respect to time only once. Okay, so again, since there is no x involved in here, this is going to be 0 after all. Okay, so that is basically 0. Okay, so those are the derivatives that you need now. I'm going to put those together. So how is the dynamics of the present value of an asset when you basically, when the asset value follows the Ornstein-Uhlenbeck process, which it does when it's, for example, stationary with regards to interest rate derivatives and all that stuff. Anyways, I mean, first off, you have negative c times e to the power of negative c times t. That's the same thing. So you see basically that's there. You need to put in basically xt into it. So that's what you do. All right. So here it is. Okay. And then you attach the differential of the process. Differential of time, which is here. Okay. So that's, no, sorry. I was starting with that one, with respect to time. Okay. Here it is. This is the expression that I just basically calculated. Then comes the derivative of the present value. I'm calling it the present value, right? So the present value with respect to x, okay? And then, of course, which is here. That's it, okay? So that's here. And then you attach basically the dynamics of the process to it. And that's it, because this is 0. So this thing is going to be 0 here in this example. Okay, thank God. All right. So that's no longer there. And yeah, so then you're done. Of course, you need to clean it up. Okay, and here I'm going to substitute by basically dynamics, which you see there. Okay, so you can simply just take it in here. And then you realize that this expression is similar to that. So they eliminate themselves. And this is basically the only thing that you're left with. All right, so you have basically just that as for the dynamics of the present value of an asset that follows, for which basically that follows the Ornstein-Uhlenbeck process. Okay, there is assets out there that might satisfy that statement, okay, when you basically look at interest rate derivatives and stuff. This is not the asset, this is just the differential, so those are the increments of that. All right? Linear trend, and then you have a constant diffusion, right? Or like the constant diffusion of the Wiener processes, but diffusion function is constant. All right, and I'm going to do that same thing for the general version, if you allow me. Okay, so it's not a big deal. This is just even a linear trend here. So you have an intercept also, okay, for the dynamics. So I'm going to repeat the same thing. I'm going to create basically, so you have the net present value, but actually this is the interest rate, so that's going to be it, all right? So basically the growth rate, you can see. So when I solve this equation, you'll see what this is going to be. So again, the derivatives are the same. I would need to replace C by C1. So if you allow me, I'm going to do that quick. So this is basically what it was, and just recollecting the results, so maybe you can check that out again. Okay, the only thing that basically comes with it is that additive constant here in the drift function. Everything else is going to be basically similar to the previous case. Okay, so the question is what happens if this is the case, but that's the question that I need to answer. Okay, so you have basically negative again. So first off, I'm addressing this expression is going to be the derivative of the function f with respect to, or the derivative of the present value with respect to time. So how does the present value change by time? That's it. This is the economic interpretation of that. Here is going to be it. So this is basically the issue. And then, of course, you have the differential of time. And then, of course, then comes this expression, the derivative of the present value with respect to the asset price, you can say. All right, so here you have the discount factor, and then of course you have just the dynamics here for the asset, okay, which is here. This is the differential here because it's going to be a constant one, okay. All right, yeah, so now I'm going to substitute here by the differential, which is here at the top, obviously, okay, so just basically there. And then you realize that this expression is also in here, but the others don't disappear. So those will remain, but basically the yellow ones disappear. Okay, so since the factor is there for those two, the factor remains as well. Okay, so then you have some basically regarding the evolution here, and that's it. Okay, some some constant, basically deterministic issue. And you might remember this. This is a Brownian motion, right? Here. This is, you know, the Brownian motion with the drift. You might remember that one. Okay? Which the present value is calculated. I haven't finished that, but you can actually stop here. This is how far you would go with this thing. Okay, guys? Yeah, I have to admit it looks horrible. And this presentation looked horrible as usually. I mean, when you see this when I saw this for the first time, I needed my time for myself. But it's not that big of a deal. The only issue is that, you know, you see the second derivatives of some sort with the differentials because of the quadratic variation of the Wiener process. And that's it. That is true for diffusions. That is true for functions of Wiener processes. Wherever basically the Wiener process is involved, you're going to see it. Even if basically you address Ito's lemma with time, okay? And these are the tools that we apply in finance when describing, for example, dynamics of asset or asset returns, using basically the differentials of logarithms, for example, which I did for the geometric Brownian motion and so on. Okay, now I'm going to stop here. And tonight I'm going to finish your exercises, which I kind of ask you to solve regarding the mock exam. Those exercises, take that with a grain of salt as the mock exam. So I would just basically collect one or two if you like. And we're going to do another subject, which was going to be the solution of stochastic differential equations. And the last part of this lecture, which is supposedly be the $1 trillion partial differential equation, I'm going to create that video. So this is just a reminder related to finance, and I would like you to ask you just to watch it. Okay, so that's going to be it. So as your homework. All right. I hope you started solving the exercises. And again, I will allow you to bring any handwritten notes of any sort, even if basically, you know, you can take whatever document. Okay, so any printed document that you have, you can bring. Okay, for the exam or into it. I think it's going to be better than if I give you my notes, which you might not like or whatever. Okay, guys, yes, there is going to be one more lecture addressing solutions of quadratic solutions of, stochastic partial differential equations, okay, among which basically I was addressing indirectly one or two. So it's not going to be that exciting. And then we're going to talk about the exam after that. All right, this is going to be it. All right, guys. Yes, that was it for today. I'll see you next week. Take care.